Good morning, mathematicians. It's a beautiful May morning, and we're going to go out and do some fishing. While we're doing so, we're going to do some applications with related rates. So, hopefully you'll enjoy this as we go through and catch a lot of fish. As a continuation of our video last time, what happens is eventually I was casting out. I created this ripple that we talked about last time, but then I reeled my line in. As I'm reeling it in, I'm trying to lure in some type of fish to bite. I'm cranking it and it's coming in, and all of a sudden, bam! Fish bites. There's a fish on. I'm trying to reel it in, and it's fighting me, and it's fighting me. And at one point it decides that it's going to run right towards me. It's going to do so at 15 feet per second. And I have to keep the line taut because otherwise the fish will probably spit the lure out and it'll end up getting off the line. So I'm trying to keep up with it. Now right now it's 100 feet of line out, and what I want to know is how fast do I have to reel the line in to make sure that the line stays taut on the fish so that it doesn't get off. In this situation, as in the last one, we're going to go through the same process we did before. So to remind you of that process, what we're going to do is we're going to read the problem, write down things that we know or given and things that we don't know that we're looking for. We're going to then take that and decide what's changing to create any variables that we need. After that, we're going to find rates for any of the variables given. Then we're going to find an equation relating them. We're going to implicitly differentiate, and we're going to solve our model. And then finally, we'll be able to give an answer to our original question of how fast do I need to reel in the line. Now, as we start off, I want to read through that again, and I'll refer you back to a link down below so that you can have that in front of you. But as we're reading through that, what we notice is that while the first couple sentences are just setting it up, having some fun, talking about how you're reeling in the line and there's a fish on, and that's a very exciting stuff, but it's not part of our mathematical model, so we don't really need to write anything down there. The first thing that we really see is that we notice that the fish is going to be swimming towards us at 15 feet per second. So now that's telling us something. So as we look at our picture, what we're going to do is we're going to say, okay, well, here's the fish. It's swimming towards me, so I'm going to draw a line from the fish pointing straight towards me, and I'm going to say that's 15 feet per second. So I'm going to denote that so that I have that information available to me in my picture so that I can keep that in mind as I go ahead. After that, we notice that it says that currently there's 100 foot of line out. So that is, we're going to draw a line from the fish to the tip of the pole and say that the line out is 100. And so we're going to write down 100 feet for the length of that line. As we continue that sentence, we notice that also the tip of the pole is 10 foot above the location of the fish. So what we're going to do is draw a line straight down from the tip of the pole to the water at the fish level, and we're going to denote that as 10 feet. And then we notice that, well, we have our picture, and the idea is that we have a line from the tip of the pole to the fish, the tip of the pole to the water level, and we're drawing the line showing how the fish is moving towards the bottom of the line from the tip of the pole to the water. So we're going to complete that, and we notice that we do have a triangle here. In fact, it's going to be a right triangle because the one side is a vertical line, the other side is horizontal, so they'll meet at a right angle. The next thing we see is that we want to keep tension on the line, so what we have to do is we have to reel the line in. So what that's telling us is that what we're going to want to find is how fast do we reel that line in. So I'm going to draw a line from the fish along the line up to the tip of the pole, and I'm going to say that that's what we want to find, so I'm going to put a question mark there. Now that we've drawn what we have and we know everything that's given to us and what we're looking for, what we have to figure out is what are some variables we need, and so that we can find an equation relating those. So now what's changing in this problem is, well, I'm going to start with the 10. Notice that the distance from the tip of the pole to the water is not going to change because I'm going to hold my pole in a constant position as I'm reeling in. So I do not need to assign a variable for the 10. However, the distance between the fish and the bottom of the pole is going to change. And so now I'm going to write that horizontal distance as some variable, and I'm going to call that F for fish. If you want to use something else like H for horizontal, that's fine. But I'm thinking about the distance of the fish to the bottom of the line from the pole, and so I'm going to call that F. Now also we notice that we're reeling in the line, so the length of the fishing line is going to change. And so I'm going to call that Now that we have our variables, what we want to do is we want to find our rates. So for anything given, we should find the derivative of that. And so let's first look at L. And so we want to find how fast is the length of the line changing over time. So what we're really doing is looking for the change in the line length over the change in time. And so what we're going to find is dl, or the change in length, divided by dt, or the change in time. And so dl dt is our question mark. That's what we're looking for. On the other hand, we know the change in the fish's position over time, and that is the distance between the fish and the bottom of that vertical line is going to be the change in f with respect to time, or df dt, and that's given to us as 15 feet per second. However, we do need to be careful here because notice that the fish is getting closer to us. That is, it says that the fish is swimming towards us. So df dt is actually going to be negative 15 in this case, because a negative derivative denotes a decreasing function. Now that we have our variables down and we have our rates down, what we need to do is we need to find an equation relating the variables. And so what we notice is that we do have a right triangle, and what we want to know is something about the side lengths of that triangle. And because we're looking at side lengths of a right triangle, we should use the Pythagorean theorem. And so what we're going to have is that, well, if we look at the side lengths, the hypotenuse is the length of the fishing line. And so we're going to get the hypotenuse squared is the sum of the legs squared. So one of the sides is 10, and that stays constant, so I can leave that as 10 squared. The other one is changing, so I'm going to write that as f squared. And so what we're getting is that using the Pythagorean theorem, the distance from the fish to the bottom of the vertical line is f squared, plus the vertical line is 10 squared, is equal to the hypotenuse squared. So L squared is 10 squared plus f squared. Now that we have an equation involving the variables we're looking for, L and f, what we need to do is, well, we want to find things about rates, so we need to implicitly differentiate. And what we want to find is dl dt. So that means we're going to take the derivative of both sides with respect to time. And so I'm going to get d dt of L squared is equal to d dt of 10 squared plus f squared. Now as I look at this, on the left hand side I'm taking the derivative of L squared, but remember L is a function of time, so this is a chain rule. And so what we get is that the derivative of the outside is 2 times L times the derivative of the inside is, well, the derivative of the inside is the derivative of L is just dl dt. So what we end up with here is the derivative of the outside is 2L times the derivative of the inside is dl dt. Note that if you forget to use your chain rule, your dl dt won't come out. If your dl dt doesn't come out, well, then there's no way to find dl dt because you have nothing about it. So if you're not getting out dl dt's here or df dt's here, you know that you're doing something wrong because you're not going to be able to find what you're looking for. Now as we continue on, if we look at the right hand side, the derivative of 10 squared is, well, notice 10 is constant, 10 squared is 100 is constant. So the derivative of the constant is 0. So the derivative of 10 squared is just 0. And then I have to take the derivative of f squared. Now f is also a function of time. So using the same process we used here, what we're going to get is that the derivative of f squared is just 2f df dt. And so what we end up with is that dl dt is 2f df dt. Now that we have that, we're ready to find dl dt right now. So right now what we know is, well, currently the length of the line is 100. And dl dt is what we're looking for, so we're going to leave that as is. Then I get 2 times f. Now notice that we weren't given f, so what we're going to have to do is we're actually going to have to find it. Now here, this was our question mark, so we don't have to worry about finding it because that's the goal of the problem. But because this isn't our question mark, we have to find some way to get that. Now since we need to find f, what we need to do is we need to go back and look over our problem and see if there's some way to find that. Well, what we recall is that we know that L squared is 10 squared plus f squared. We know L right now, so we should be able to find f right now. And so if we plug in L, we get 100 squared is equal to 10 squared plus f squared. And so what we have is that f squared is in fact equal to 100 squared minus 10 squared, which is f squared is 10,000 minus 100. So f squared is 9,900. And now if we take the square root, what we get is that f is approximately equal to 99.5. Now that we found f, we can go ahead and plug that in. So we had f was 99.5. And then we just need to say that df dt, remember, was negative 15. So we plug in negative 15. Alright, so I erased some things so that I had a little bit more room. But now what we need to do is just solve this equation for dl dt. So really I just need to divide by 2 times 100 is 200. This cancels out. And we get 2 times 99.5 times negative 15 over 200 is going to be dl dt. And that's approximately negative 14.9. So now what we've done is we've solved our model, and we've shown that dl dt should be negative 14.9. Alright, now that we've found that dl dt is negative 14.9, what we want to do is we want to go back and find the solution to the original problem, which was how fast should I reel the line in? Well, what this is telling us is that the distance between the fish and the tip of the pole, or the length of the line, should have a rate of change of dl dt is negative 14.9. What that means is that L is getting smaller at a rate of 14.9. And so what we need to do there is we need to find the units. Now, the units for length were given to us because F was, or df dt was 15 feet per second. So what we're telling us is that our distances is in feet and our time is in seconds. So again, L is a distance, this is going to be in feet divided by seconds. And so what we get is that dl dt is in fact negative 14.9 feet per second. So what does that mean? Well, that means that the length of the fishing line is decreasing at a rate of 14.9 feet per second. So now if we go back and try to answer our original question, what I would say is that in order to keep the fish line taut, we need to reel the line in at a rate of 14.9 feet per second. And so that's what we would need to do in order to keep the fish on the line so that it doesn't spit out our hook. Thank you for joining me today. I hope you enjoyed these applications. If you did, make sure to like this and let me know. If there are any other situations that you'd like me to look at, also let me know in the comments below, and I'll be happy to try to do a video for those. While you're at it, make sure to subscribe to the channel so that you are updated on all the new stuff that comes out.